So if you've seen any of the scanning tunneling microscope projects or the notes I've been putting together on STMs, you'll know that you need to get a piezo buzzer and you need to cut it into quarters, basically. And it's kind of not. I find it not very easy to do just by hand, with a box cutter. And I've been thinking about ways to do it in a more repeatable kind of fashion. And I thought about a number of things. I tried using actually a very low power laser cutter, like a laser etcher, and that didn't work. And I was thinking about CNC milling the buzzers, and maybe trying like a higher powered, like a 30-watt laser, to see if that would work. But the way I'd done it before is just using a box cutter, and that works, but it's just a pain to do. And I figured what I'd do is design a jig to see if I could make that process a bit easier, and it seems to work like surprisingly well. So 3D printing is now really cheap, particularly SLA printing, mail ordered. You can get precision parts made, and these parts were, I think this was like $10 and this was like $20, so it's not hugely expensive. And I use Onshape to design everything, and I get these nice robust little parts. So I figured, this will be a nice project to do for the buzzer. So I designed this jig, and you just put a standard box cutter blade into the jig, and then you can mount the buzzer in this depression, and the whole thing kind of screws together. If I can find my screwdriver, and it keeps it all in proper alignment. Which is obviously the thing I have doing. So then the cutter kind of sits inside, and you can just cut along, and you can dig into so you can hopefully hear that scratching away. And you can dig into it, and I found it's quite easy. You have to give it a few. You're not just going to do a single cut. The piezo material and whatever it's sitting on is fairly thick, but with a few cuts you can get in there. And as you're doing the cutting, actually enough of the piezoelectric material is exposed that you can get in there with some probes, and you can check the continuity, which I think that will still be connected. Probably they'll all still be connected. But you can check the continuity as you're cutting it, so you can see that if you've completed. Let's see if we can get at least one. But it all stays in nice alignment, and it works quite well. And the cutter itself is 0.5 millimeter thick, so I was worried when I was kind of designing the jig that that 0.5 millimeter void or slot that the cutter sits in wouldn't actually come out. It would just be joined together when it was printed, but it came out really well, and everything fits together quite well. It took a few times cutting through to get it wide enough. I guess the slot is, I didn't add any a leeway on there, so it kind of just fits in exactly. But because the material is relatively soft, after a few cuts through, it widens out a bit, and it fits in quite smoothly. So yeah, that was all testing. Continuity was fine. So there it is. Then you've got your buzzer cut into the four corners, and then the way I do it is I just lift it up with a cutter, and there it is. And I did the continuity test as I was cutting it, and it was fine. So a few others I've done, it all works out really well. This kind of aligns it. You know, the buzzer sits in that void, so it's always going to be aligned to the metal disc. But quite often the piezoelectric material is not patterned centrally. So for that, I do actually have another jig that that sits in the same system. But you can move the piezo buzzer around, and then you can just screw it down to clamp it in. And I use that for one of these, but I think probably this alignment is good enough. There'll be some more experimentation to come, but yeah, there we go. That's the jig. I'm kind of thinking about putting it on my shop, so I will add a link to my shop in the description. Yeah, I'll also probably make the free. If anyone wants to design anyway, just ping me. Send me an email, new@sgenomics.org, and I'll send you the STL files.